Hello everyone. Today we are going to introduce our ACL main conference work entitled Scale Towards Collaborative Content Analysis in Social Science with Large Language Model Agents and Human Intervention. Content analysis is a key research method in various disciplines. It breaks down complex and unstructured text into numeric categories based on theory-driven rules, offering a systematic and quantitative approach to interpreting sophisticated information. Particularly in social science, content analysis is usually labor-intensive and time-consuming. It often requires a team of researchers to manually annotate sizable datasets, conduct comprehensive discussions, and iteratively refine coding rules in multiple rounds to ensure the reliability and validity of findings. This artificial process, while rigorous, presents two challenges. First, it relies heavily on domain-specific knowledge and individual scientists, potentially introducing subjectivity and limiting generalizability. Second, the substantial human resources demanded by content analysis tasks make it difficult to scale, especially as the volume of digital data expands exponentially. In this paper, we propose Scale, a novel multi-agent framework to simulate content analysis via LLM agents. Scale imitates key phases of content analysis, including text coding, collaborative discussions, and dynamic codebook evolution, while capturing the reflective depth and adaptive discussions of diverse human researchers, thereby reducing subjectivity and improving scalability. Moreover, by incorporating different human-AI collaboration modes inspired by social inference theories and human-computer interaction theories, our framework extends multi-agent interactions with human expert intervention. This potentially mitigates algorithmic bias and strengthens contextual sensitivity, making it suitable for a wide range of social science content analysis tasks. The method unfolds in four primary steps summarized in the figure. In Figure A, prior to the content analysis task, we set up both LLM agents and an initial codebook. We begin by configuring several LLM agents, each emulating a seasoned social scientist through a system prompt that incorporates distinct personas. These personas based on real-world social scientists facilitate authentic role-playing. In Figure B, LLM agents convert text entries into numerical categories by applying theory-informed rules from the codebook. Each agent is assigned an identical batch of text entries from the text dataset and works autonomously to classify each entry into a discrete category. In Figure C, agents engage in collaborative discussions to resolve discrepancies in their coding outputs. Due to the initial ambiguity of the evolving codebook and the distinct personas embodied by each agent, it is not uncommon for agents to generate differing annotations for the same text, which mirrors the subjective nature of real-world content analysis. Whenever an agent's coding diverges from the consensus, the agents initiate a structured discussion up to a maximum of rounds. During each round, they update their annotations along with explanations based on peer opinions until they converge on a unanimous decision or reach the limit on discussion rounds. Once a text entry is finalized, the agents will move to the next entry. In Figure D, agents refine the codebook by incorporating insights from their discussion. As noted earlier, the initial rules can be ambiguous, overlapping, or insufficiently detailed to cover all categories. To address these issues, we introduce an iterative codebook evolution process grounded in domain expertise. Specifically, the evolution approach offers two strategies. One enriches existing rules by adding clarifying examples and explanations, whereas the other allows for adding, removing, or modifying rules to dynamically adjust the set of categories. In practice, agents first propose an updated codebook, then engage in multiple rounds of discussion to refine it until consensus is reached. The finalized codebook subsequently guides the next task cycle. Importantly, agents may also retain the current codebook if no changes are warranted. We further augment scale by integrating diverse human intervention modes that empower domain experts to provide targeted feedback and instructions. Depending on the scope that human experts can control, human intervention can be categorized as targeted versus extensive. For targeted intervention, the scope is limited to the agent discussion phase. The process is done with less human oversight, while extensive intervention can be applied to both the discussion and codebook update phases. Further, intervention can be formulated as collaborative or directive based on the role the human experts play. For collaborative intervention, human experts are involved as collaborators, while under directive intervention mode, human experts serve as the absolute authority. Our experiments leverage 5 real-world datasets, each meticulously annotated and validated by social science experts. These datasets are organized into 7 distinct tasks that encompass both multi-class and multi-label classification challenges. Our multi-agent system is built on GPT-4o and GPT-4o Mini. For each backbone, we explore 4 prompting strategies: vanilla, chain of thought, tree of thought, and self-consistency. We first assess the performance of automatic content analysis without human intervention. Table 2 reveals that scale using GPT-4o achieves satisfactory results across a diverse range of tasks and prompting techniques with an average accuracy of 0.71. Notably, different prompting techniques offer distinct benefits. Compared to the vanilla model, self-consistency prompts boost the labeling accuracy by 3.2%. However, in certain cases, for example CNNP, COT prompts lead to a significant performance drop. Furthermore, as expected, GPT-4o outperforms its distilled version, GPT-4 Omni, by an average margin of 13.6%. For the human intervention framework, it shows an average improvement of 12.6% over content analysis without human intervention, demonstrating the importance of human intervention. Specifically, interventions in the directive mode prove more effective than those in the collaborative mode, leading to a 13.1% increase in coding accuracy. Similarly, extensive interventions generally outperform targeted interventions, yielding a 15% average improvement. This aligns with the intuition, as human experts can contribute more domain knowledge through intervention across a broader range of agent behaviors in a mandatory manner. Lastly, the benefits of human intervention also vary by task. CES task sees a 19% improvement, whereas the FWPE task shows a 4.9% relative gain likely because the CES task is more domain-specific and subjective, thus more responsive to expert insights. In extra investigations and case studies, we designed several research questions. To answer what designs can enhance content analysis performance of Scale, we analyze how Scale enhances content analysis tasks by considering the number of texts B, discussion rounds K, and agents N. We found that a moderate number of texts produces the best accuracy. Scale achieves better performance with K is greater than or equal to 3, as more rounds better facilitate consensus among agents, thereby improving coding accuracy. In general, increasing the number of agents improves coding accuracy, as more agents bring diverse perspectives, fostering more comprehensive discussions. To answer how does the discussion between LLM agents impact coding results, we conducted a discussion analysis using both qualitative statistics and illustrative examples. Figure 4 reveals that inter-agent discussions substantially boost consensus, enhancing the average agreement rate by 41.1% across all 7 tasks, and overall content analysis accuracy by 15.4%. In this work, we design additional research questions, such as how reliable are the codebooks proposed by LLM social scientists, and to what extent can LLM agents simulate content analysis and do more qualitative and quantitative analysis. For more information, please refer to the paper. Here we provide some resources. Please do not hesitate to let us know if you have any kind of questions. Thank you so much for your valuable time for attending this talk.